Hi everybody. In this video we will see how to perform a finite element analysis of a fiberglass fabric impacted by a spherical projectile. Now if you have not done already, please watch my video on how to construct this geometry. You can find this on the top right corner of your screen. I have added 5 additional layers to the original geometry by transposing to the total fabric thickness of 1 millimeter. Next, we will construct the geometry of the spherical projectile. Feel free to jump on the beginning of the 4th minute of this video if you know how to do that. We will be taking advantage of the symmetry of the normal impact and the fact that the geometry is also symmetric in the YZ and XZ planes. So we'll only model 1/4 of the whole system, so it will be less computationally expensive. Okay, let's now see how to model the spherical projectile. We will use self-discretization in order to decrease the number of elements in the system. In order to quickly construct the geometry of the spherical projectile, we go to the mesh shape mesher on the element and mesh tab, give a radius of 11.5 millimeters and a density of 20, which is the density of the mesh. And the center of the sphere will be at the origin of the coordinate system. Give a name to the part. And as we can see, this is fine. We will remove the 3/4 of the elements. Okay, we have it ready. Now we will delete the elements by going to the Element Edit tab. First, we have to know exactly how they align, how the elements align, if they are symmetric or not. So we go Element Editing and select the unnecessary elements to delete. The last part in constructing the geometry is to transpose the spherical projectile in the Z direction. Perfect, our geometry is now ready. Next, we will apply boundary conditions and create sets that will be later used for interactions between the bodies. We will begin with our boundary sets. Select the nodes that will actually have fixed boundary conditions. and then we select the nodes that will have symmetry boundary conditions. Good, now we can create sets for the interactions. We will first create a cell set for the project type. Next, we'll create a node set for all the nodes in the yarns. This will serve for the interaction between yarns, so yarn-yarn contact. Perfect. Now we have the sets for our interactions. The next step is to define the elements for the yarn geometry. In order to do so, we go to the section beam and define the elements as element formulation 1, which is a Hughes Liu integrated beam formulation. The strains based on the curvature and relative nodal displacements is calculated at the integration points. And then based on the constitutive relationship of the material, from the strains, the stresses are calculated. Now, the number of integration points in the cross-section is defined through the QRIRID parameter. This is arbitrary to you. Of course, the accuracy will increase with increasing the number of integration points in the cross-section. I will use number 3, which is the Lebato quadrature. It's a 3 by 3 integration, numerical integration theme. And then in CST parameter, we can choose between rectangular, tubular, or user-defined cross-section. Now, we know that the yarn cross-section shape is elliptical, but for the purpose of this tutorial, we will assume a circular shape with the diameter of the circle equal to the minimum diameter of the ellipse. We will later scale the material properties to match the axial stiffness of an equivalent elliptical shape. Of course, the bending stiffness will be different, but we assume that the yarn bending is not the dominant energy absorbing mechanism, but rather the stretching is. You can see the integration beam card for more complex cross-section geometries. Next, we define the outer diameters of the yarns as 0.09 millimeters, with the inner equal to 0. Now that we have described the cross-section of the yarns, next we go and describe the material behavior. Since we are considering fiberglass, we'll assume the material behaves elastically and fails by brittle failure at the threshold stress. The material properties will be scaled differently for the weft and warp directions due to their different cross-section areas. And the threshold stress will be defined as the maximum principal stress through the mat erosion card. We have created the cards for the material properties of the yarns and the cross-section. So now we can define the parts and link these cards to the parts. Now we'll be doing the same thing for the projectile. We have to create the section and material cards. First we go to the section, we create a card for section shell. We give it a section ID, we leave the element form in default number, we define the thickness of the cell as 0.1 millimeters. Next, we will describe the projectile. We assume that it will not deform upon impact with the fabric, so we will define it as a rigid material behavior. So we'll only give density and Young's modulus and the Poisson's ratio. The next part is very crucial. We need to define the interaction between the yarns and the projectile yarns. The contact between the fibers can be defined with the automatic general contact card by placing the fibers into the slave section. Beam nodes should always be defined in the slave section. I will not add any static friction coefficient or dynamic friction coefficient here. Just remember that if you want to define the dynamic friction coefficient, you will need to first define the decay coefficient, the third parameter dc, since the formulation for the friction coefficient is given by this formula. The fabric elements are expected to erode and fail. That's why we will define an eroding nodes to surface contact card, where the slave will be the fabric nodes and the master will be the cell elements. Now, in some contact types, LS needs to know where the symmetry lies and which nodes are affected. For that reason, there are three different parameters in row 7. We will be changing for the beam elements the two first. The next step is to define the initial kinetic energy of the projectile. In order to do that, we go to the initial velocity region. I will then define the z component of the velocity equal to 300 meters per second. Okay, now we are close to the finishing line. We can define some outputs that we would like to see after the analysis is complete. We are ready now. Let's run our analysis and see some of the results. That's all from me now. Thanks for watching, guys.